Hello, I'm Steve Freeman, and over the next number of lectures in this video, I'm going to try and explain to you about the brittle failure of ceramic materials, and perhaps better yet, how to do the testing and how to do the analysis to ensure that you will not have failure. Ceramics are wonderful materials. Those of you who work in our industry recognize this because of their high temperature properties, their hardness, their electrical properties, their optical properties at times, their transparency. We use them in many different applications. But they have one serious drawback. They are brittle, which means that they can fail suddenly under stresses that we don't recognize are present or which are there for other reasons. And you notice on this screen that I have included my email address, and I hope, because I have limited time to go over all the many details of brittle fracture, that those of you who have questions or want more explanation will contact me, and I will be happy to follow up with more information. So with that, why don't we get started and move right into the lectures themselves. First of all, I want to reiterate, brittle and ceramic are pretty much synonymous. That is, almost all ceramics are brittle materials. And I define ceramics, and I've explained this for many years, that I call them any inorganic nonmetal, and that will include materials such as glasses, single crystal, semiconducting materials, etc. So there are a wide variety of what perhaps we don't consider as traditional ceramics, which will behave in exactly the same way in terms of their fracture susceptibility. So let me first talk about what I'm going to talk about, namely give you a course outline. There are a series of lectures, and I've titled each of them. So the first lecture is really some broad explanation of brittle failure, its causes, a brief history of how we came about to know what we know about brittle fracture, and some introduction to the technology, the science of fracture mechanics, which is really the key to being able to understand the fracture behavior of materials and to understand the physical mechanisms why these materials behave as they do. Talk some about measurement procedures and applications as well. Second part will be on a process, a phenomenon that occurs in ceramic materials. It does occur in metals as well, but its mechanism is quite different in ceramics, a term that we call environmentally enhanced crack growth or stress corrosion, which maybe some of you have heard about. So I want to talk about a little bit about the historical background, what we've learned over many years, 70 or 80 years of research into this phenomenon, and some effect of composition, environment, and temperature on the behavior, what the molecular mechanisms are, and some of the unknown aspects of this particular phenomenon, which is very important because it can lead to what is called delayed failure of materials, and I'll go into that much more later in this series of lectures. Part 3 is a fairly short addition to what I have talked about earlier, and that is modeling. And that is, can we predict from molecular or atomistic models of materials what might happen to them, what stress will cause failure, and so forth. This will relieve a lot of the difficulty in measurements and makes use of our ability to do atomistic calculations to avoid difficult testing of various materials in search for the best solution to a problem. Part 4 is a particularly important one because it talks about how we should go about measuring strength and analyzing the strength behavior of ceramic materials. And as you see here, I'll go through a number of test procedures, both flexural, tensile tests, and lastly, maybe the most important is data analysis. How do we understand what the strength data from our series of test specimens really means and project that to predicting what might happen to a large number of components that we might make from that material. Part 5 is on fractographic analysis, and the word fractographic means when a material breaks, there's a particular pattern produced on the fracture surface of the material, and there's a great deal of information about why the material broke, from what it broke, and maybe more important, at what stress it broke. So we can understand that by looking at the patterns on the fracture surface, and I'll talk some about how we go about doing this. Part 6 is also particularly important and pertinent to ceramics, and that is, how does their microstructure affect both the resistance to crack growth, namely what I call fracture toughness, we'll talk about that more in a few minutes, and on the strength. Ceramics, unlike metals, the resistance to crack growth is so low that the crack sizes that cause failure are typically of the same size as the microstructure of the material itself. So that's why microstructure for ceramics is a particularly important topic when we talk about brittle failure of these materials. And then I also want to talk about a particular kind of failure, namely thermal shock. Many of you have experienced anytime you quench a glass in water or heat your teapot too hot, things fail. And thermal shock failure is a particularly common kind of failure in ceramics. And I'll just talk a bit about the test procedures and why this might occur and the best procedures to go about understanding how to avoid such thermal shock failures. The final lecture is on determination of reliability and how we might do safe design for ceramics under stress over long periods of time. I mentioned earlier about cracks growing slowly with time, and so this determination of reliability over time is particularly important, and I want to show you a few ways in which we can use the data that we get from laboratory tests to predict the reliability of our materials over fairly long periods of time. And then finally, I'll just summarize by saying what I think we've learned out of these series of lectures, and then end a bit with what needs to be known. Surprisingly, after all these years of research into brittle failure, there's still a lot of aspects that need further elaboration, and I'll mention some of that. So with that, let's just dive right into looking at this idea of brittle failure. And what I mean by brittle failure is that fracture occurs without any noticeable deformation before fracture. We think of metals as failing, and when that happens, there's a curve over in the stress-strain curve that you see here. In brittle materials, that doesn't happen. There's a sudden failure, and the load drops to zero at some point. And so we don't get any warning of this kind of failure. The piece just breaks in two, and this can be catastrophic depending on the kind of material we're dealing with and what the application we've put this ceramic in. So what do we mean by brittle exactly? It means that there are none or very few mechanisms that relieve stresses. In other words, metals are ductile because there are these dislocations that can relieve stresses. There are strains that occur in the material, and with ceramics there's no such mechanism. There are no mobile dislocations. Viscous flow doesn't occur, at least at room temperature. So when there are sharp cracks in the material and there are sufficient stresses at the tip of that crack, failure will occur immediately. And I said this earlier, but brittle materials that behave in this way include glasses, single crystals, ceramics, but also rocks and concrete, some metal alloys, and could also include metals at low temperature. And the application that's usually shown is this picture of the tanker Schenectady in the 1940s, which was sitting in harbor, and in very cold water, that metal, the steel in the ship, became brittle, and the ship simply broke in half. And this was one of the motivations for the instigation of studies at the Naval Research Laboratory at the time into brittle failure, and some of you might have heard of Dr. George Irwin there, who is really considered the father of fracture mechanics. And this is really some of the reasons why fracture mechanics became so important, to understand why brittle failure occurs under some conditions. And you'll hear more about this, or a lot more about this later on. So what are the kind of ceramics that we look at, what I call technical ceramics, that are susceptible to failure? Some of you think of structural components, the gas turbine engines. In fact, for the power industry, in some cases, use ceramics as turbine blades because they're lighter weight and can operate at higher temperature. So these ceramic materials, typically made of silicon nitride, are also susceptible to brittle failure. Again, Sonar transducers, either ultrasonic transducers or sonar transducers used in the Navy, can fail, and they are piezoelectric materials that fail by brittle failure. Any windows, what I call windows, the glass windows that you see in your homes or other applications, infrared transmitting windows, anything in which radiation can pass through, are typically made of brittle materials. As I say, glasses are ceramics in the broad sense of the word, and brittle failure is a frequent cause of failure in these materials. Glass fibers, which we use for optical communication, are obviously brittle, and we have to be concerned about failure of them. And even electrical components, things, multi-layer capacitors, of which you have thousands in automobiles, electrical insulators that you see on lines everywhere, all of these materials are potential candidates for brittle failure. And so you can see that what we're going to talk about over these series of lectures are very important to a wide variety of materials, a wide variety of applications. So what can cause the failure of these materials? Well, the obvious thing is mechanical loads, structural stresses of one kind or another. But interestingly enough, electrical fields can produce stresses in materials, in capacitors and transducers. Thermally induced stresses due to temperature differentials. I mentioned thermal shock. I'll talk more about that later. And you might recognize that impact due to rain or dust on a material can produce damage, which under fairly low stresses can also produce failure. Why can this be important? Because, first of all, if I don't know the failure stress or understand the failure behavior of my material, how do I choose the best material for my application? Also, how can I predict its reliability? I've chosen a material and I think it's going to suit my purposes, but how do I know it will last for the period of time in which I need it? And the safety of the material. Will my part survive for a required period of operation without causing catastrophic failure of some other portion of the application? So let me talk about when I'm going to design. If my boss comes in and asks me to design a particular component, there are two sides to mechanical design. First of all, there's the mechanical properties of the material itself. Its elastic properties, elastic modulus, its fracture resistance, which we're going to talk a lot about, the damage state in the material, either damage due to the way I made it or something happened to it during operation, and the susceptibility to time-dependent failure, which I will talk about a lot more in the next lecture. And the other side is obviously the operating conditions. What are the stresses, the magnitude, the location, the time variability? If I'm looking at windows, how hard does the wind blow, over what period of time? These are all important variables. What's the geometry of the part? What's the environment? Is it operating at low temperature? Is it operating in a moist environment? These are all important things that I need to think about as I go about choosing materials for any particular application. But there are other issues as well. First of all, the effect on the primary application. Obviously, the weight of the material is going to be important. I can't over-design. I can't afford to do that. I can't make the part too heavy. I can avoid failure simply by making the part large enough, but that probably isn't going to be very useful. What is the required lifetime? Is this a part that's just going to see a few minutes of operation, or is it going to be in place for years? Something to think about. What are the consequences of failure? What are the dangers to personnel around it? What costs will it be to replace the part? These are things I need to think about as well. And what level of confidence do I want? If I'm going to be 90% sure that I'm okay, that's a lot different than being 99.99% sure. And I'll show you later how one goes about assessing that kind of level of confidence. We also have levels of uncertainty over what we're doing. What are those sources of uncertainty? We're going to go in the laboratory and make measurements because that's the way we can develop the data to predict what might happen to my material. But there's always measurement error. One can't avoid it. There will be uncertainty, and particularly in strength measurements, and I will talk a lot about that later. There are uncertainties in every strength measurement that I make for one reason or another. So what I call that is measurement error. And this leads into the statistical nature of the data that I'm taking. I can't make unlimited numbers of tests. I have to choose the number of tests I make because of the expense, because I can't find enough material to do the tests on, et cetera, et cetera. So the limited availability of data also means there's an uncertainty in any prediction that I make from that data. Can something happen that I didn't recognize might happen? In other words, I mentioned impact. I don't necessarily always design for impact of a large object. If somebody throws a baseball at my window, I'm unlikely to have predicted this in my assessment of how strong a window I need, but you can understand that failure can occur due to something like that. And then the model. We'll show you later that we base most of our predictions of fracture based on some model, which I call physics. In other words, the relationship between the stress that I apply and the fracture itself is a model. And it's only a model. And so there can be some uncertainties in the model itself, and these can lead to uncertainty in my predictions. So you recognize there are a whole series of events that could happen, or ways in which things can lead to uncertainty in the reliability of what I have. And finally, I have to scale up. I do a whole series of tests on my laboratory test specimens, but then I have to predict what might happen to a component of an entirely different shape, a different size, and probably containing a lot more material, and there are a lot more parts than there were specimens. So I will show you later how we go to that. So now we'll go into a lot more detail into fracture. And I found it interesting that the study of fracture of brittle materials goes back a long way into history. And if you notice here at the top, and I don't expect you to memorize this, it's for your own interest if you want to look them up. The earliest reference I could find to any brittle fracture was 1859 on bursting stress of glass bulbs. But you can see that through the early years there were some, not a lot, of studies into the fracture of brittle materials, and mostly glasses. And why glasses? Well, glass is both homogeneous and isotropic. We don't have to worry about microstructure, which we're going to talk about later. And so it makes an ideal test material. It was easy to make glasses, and so there's a lot of work in the literature on glass as the material of choice to investigate the mechanism of brittle failure. So then, how does fracture begin? First of all, I want to point out that almost every specimen or component that you have contains flaws. And I think we want to get this out of the way fairly early. The flaws are not, we mean, manufacturing defects. We mean because the resistance to fracture of ceramics and glasses is so low that there are typically small surface cracks of the order of a few microns produced during machining or polishing that are the real source of failure. And while it is possible to avoid these or make them infinitesimally small, such as in glass fibers, typically these are what we're looking for in most failures. But there can be failures from unwanted large grains, pores or inclusions, incomplete sintering, things of this sort, or, as I continue to say, if there's an impact on the particular component during use, this can be the source of failure because the impact produces these small surface cracks. So we're going to talk a lot and use the word flaw throughout this series of lectures, and I just wanted to get it out of the way what we mean by flaws. So yes, they can be defects, but 99% of the time they are caused by the way we made the part itself. If there were no flaws in the material, almost any material would be extraordinarily strong. You can calculate what it would take to pull atoms apart, and you could see from that that it would require a very large stress to produce the failure or to produce two pieces from one. But it was recognized, and Inglis in 1913 was really the one who first put forward the idea of a stress concentration. He did it for a elliptical void in a material, and pointed out, calculated that because of the void there was a concentrated stress. You see here at the bottom the sigma sub c. That meant that the far field stress, as denoted by the arrows on this small piece, was concentrated at these points in the ellipse, and therefore the actual stress at these points was a function of the size of the void and the radius of curvature at these points. And this meant that failure could occur at much lower stresses than would be predicted just to pull atoms apart in the piece itself. This was followed, and maybe the most important reference that we have to brittle failure comes from 1920 and Griffith's introduction of the concept of the statistical failure. He, in fact, worked in the aircraft industry and sort of on the side did a lot of work on glass fibers because he was interested in it. The aircraft people weren't that thrilled with that, but it worked out to our advantage. What he did was measure the strength of glass fibers as a function of their diameter, and he came up with two major findings, both of which we use today and we'll go into a lot during the course of these lectures. First of all, that the strength was statistical, namely the larger the fiber diameter, the lower the strength he found, because there was a greater likelihood of encountering one of these flaws in the material. And secondly, and we go into this a great deal in the chapter on the idea of cracks growing under stress, is that the resistance to the growth of the flaw was determined by the energy needed to create the fracture surfaces. And the expression he came up with was the fracture strength was related to the elastic modulus, something that he would call the fracture energy or fracture surface energy of the material. And the material itself then, A would be the flaw size, and this expression, although the numbers that he used to put into this to corroborate what his model looked like weren't quite right at the time, the form of this equation holds to this day. This kind of expression we'll see a great deal in the course of these lectures. So, and in fact, more details on the growth of the kind of flaws that Griffith encountered will constitute a great deal of part 2 of this series of lectures of this course. Well, we talk about how we did research, and there was a lot of work into trying to understand brittle failure, how to understand why pieces failed over time. But before the discovery of fracture mechanics, there were several problems in understanding the fracture of glasses, which is again the primary material that was looked at, because the only measure of material's resistance to failure was its fracture strength, usually determined in bending. This is prior to about the 1960s, and because of the statistical nature of strength and our inability to actually see the crack directly, researchers were unable to determine why this crack was growing. They knew that failure occurred over time and that it depended on things like environment or stressing rate or size, but why that should be so and what was really happening within the material itself was unknown. There was no way to interrogate the material directly ahead of this growing crack. With the development of fracture mechanics, and I mentioned George Irwin's name earlier, he introduced the concept, what was called strain energy release rate. Namely, you see a little specimen that I show right here. In his case, he looked at metals. I mentioned earlier about the failure of brittle metals as well. So if one pulls on this specimen, there is a small notch introduced, and that notch and a small crack at the end of it will grow with time. And the term that he coined was strain energy release rate. G, I won't go into the reasons why he called it this, was related to the load I put on it, P, the thickness, B, into the screen that you see, and the change of compliance in the specimen with respect to the size of the crack itself, so DC, DA. And so given this kind of configuration, what he called G sub C, strain energy release rate, is very equivalent, and I'll show in a minute how it's related to the fracture energy that Griffith introduced many years earlier than this. And then by definition, the G sub C is equal to that twice the fracture energy that Griffith introduced. So this works in our favor in terms of analyzing all of our fracture that happened. So this is really the beginning of the development of fracture mechanics. Some of you have heard of the term stress intensity factor, and I'll just take a moment to define what that is. If I apply a stress to a specimen, say, in some load, what I call far field. In other words, I pull on the specimen, I apply a stress in some fashion, then the stress near the crack tip, and I'll show in a moment it's not right at the crack tip, but it's very close to the crack tip, is related to this, what is called a stress intensity factor, and that stress intensity factor decreases with distance away from the crack itself. And these angles, it also decreases into the plane of the screen that you see, but that we won't go into that. There are a lot of details involved in here. Fracture mechanics is a very complex subject, but the idea of defining stress intensity factor is really the slope of a curve of the crack tip stress as a function of distance away from the crack tip itself. And there are actually 3 modes in which I can apply the stress, and there's a stress intensity factor associated with each of these modes. The opening mode, which we're probably most familiar with, we simply pull on this and the crack moves in this direction. This is called mode 1. In mode 2, there's what we call in-plane shear, and you can see what happens. There's a shear stress applied, and this grows the crack in the same way. Or there's what we call mode 3, which is out-of-plane shear, and you can see the crack growing in this way. In this series of lectures, I'm going to only talk to you about mode 1. There's still a lot of work going on in mode 2 and mode 3 failure and how they contribute to the fracture of brittle materials. And my colleague and I, Jack Pachowski and I, in our book on fracture of brittle materials, go into a lot more detail on that. But the time and the detail permitted here won't allow us to look at too much there. And to be honest, for the most part, everything that you're going to want to know about happens in mode 1 failure. I think so we're safe just talking primarily about that. However, one of the things I should say is that we say that brittle materials have no plastic flow, no dislocations at a crack tip. But the fact is that very near a crack tip, there is a nonlinear elastic zone. We don't really know how large it is. It can be a few atoms in extent, but the elastic modulus is not completely equivalent to Young's modulus all the way into the crack tip. So there's a non-elastic zone, if you will, right near the crack tip. However, the beauty of fracture mechanics is that we can be used to explain fracture despite the existence of this non-elastic zone, and the people working in fracture of metals do this to a great extent. We don't worry about it so much in ceramic materials because the size of the zone is so small that we pretty much ignore the fact that it exists. However, it is possible, and this is something that's really unknown, that differing zone sizes from one ceramic material to another can have an effect on fracture. But we're really not sure at this point. A lot more research is going to be needed to understand what the effect of that differing zone size might be. But just to recognize that no material is linear elastic up to the point of the crack tip itself. Let's come back to this idea of a flaw. Throughout fracture mechanics, flaws are modeled as semi-elliptical cracks, or vice versa. So you can see here what the shape of this semi-ellipse is. Typically, it will be with a long axis. If this is the fracture surface of the material, then the long axis will be parallel to that fracture surface, and the stress will be into the interior of the material. So the stress intensity factor will be a maximum at the minor axis of the ellipse down here. There are kinds of flaws, and you see them in practice, where the ellipse is a different shape, namely the minor axis of the ellipse is on the fracture surface, but the concept is the same for either one. And to give you an idea what a real flaw might look like, and we'll show this later in the section on fractography, that flaws look exactly like that in many cases. This is a glass flaw, and you can see here the semi-ellipse of the original flaw, and these ideas of fracture markings on the surface, which we'll talk about later. And that I'm going to show you later that there's a great deal of information on the fracture surface about the fracture behavior of the material and the stress at fracture. So here's the key equation now. Strength is proportional to that term fracture toughness. What do we mean by fracture toughness? What we mean is the stress intensity factor when fracture occurs. So here is the equation that is key to our understanding really of brittle failure in most materials, is that the fracture stress, the strength if you will, is related to that critical stress intensity factor, which we typically call fracture toughness, the inverse square root of the depth of the flaw into the surface, a to the minus 1/2, and this y factor, which is related to the shape of the particular flaw that caused failure. And for many types of loading on a flexure specimen, although it can change if you load it differently, this factor is about 1.12. Now, traditionally in fracture mechanics literature, there are two kinds of stress intensity factors. One in what we call plane stress, and there the stress intensity factor is directly related to the elastic modulus times, again, this strain energy release rate, or as I've shown before, twice the fracture energy times the elastic modulus, or something called plane strain, where it's related to E times the strain energy release rate, but it contains a factor containing Poisson's ratio. Typically in the literature, we've ignored that Poisson's ratio term. For better or worse, Poisson's ratio in ceramics ranges from about 0.2 to 0.3, something of this sort. But we simply have not taken that into account in most of our analyses of fracture. It's my opinion that probably has not made a great deal of difference in what we have learned or in our prediction of failure, but just so you know, there is this factor that needs to be taken into account in many cases. Well, now I've talked something about this critical stress intensity factor. It's a very useful parameter, but very hard to define exactly what we mean. And in the next couple of slides, I think I'll try and show you why that is. First of all, I'll give you a general definition. So for a brittle material in which no environmentally enhanced crack growth occurs, I say we, but others too, define fracture toughness, or that critical stress intensity factor, as the stress intensity factor at which a crack begins to grow. And there's still argument in the literature over whether that's the right definition, but I think it's a useful definition for at least we who are doing engineering work with these materials. It enables us to pick out exactly how we want to measure things. And I make the point here that critical stress intensity factor for any given material is not a fundamental constant, but is measurement dependent. And I'll show you lots of measurements in the next few slides. And because most materials do undergo, I showed up here, I said if there's no slow crack growth, what I call environmentally enhanced crack growth, slow growth with time, then this definition works well. But for many materials that do undergo this, then that's a problem, because then there's a slope to the curve and we have a little more difficulty. And so then critical stress intensity factor becomes 1 point on a plot of crack velocity versus K1. And I show this schematically as follows. So what fracture toughness means for an actual material, here we've plotted the growth rate of the crack velocity, as a function of stress intensity factor. And you can see the crack is growing slowly with time. It speeds up and the slope of this curve increases, but it's still a finite curve. And the critical stress intensity factor is just 1 point on that curve. And what I measure in a test like that is really where the machine can't follow the stress movement, depends on the environment, depends on the slope of the curve. This is fairly steep, so I don't make too much error depending on where it is. It typically occurs around 1/10 of a meter per second, something of that sort. But just to make the point, It's not absolutely defined. It's only defined by the test procedure itself. So again, just reiterating of some of the things I've already said, the value of that fracture toughness number will depend on the test environment, will depend on the loading rate, and as I just said, it's something between 1/100th of a meter per second and 1 meter per second where criticality occurs. And I'll say a lot more about these kind of curves in part 2 when I talk about environmentally enhanced crack growth. How do we use, now that we know what fracture toughness is, and I will show you later how we measure it, how do we use it in our engineering profession? Well, it's interesting. Critical fracture toughness isn't really used directly in the design of most components. There are better ways to do it, namely strength, but there are conditions and cases where the application demands that I find what the critical fracture toughness is. I'll show those. But it can be used to rank materials. For the most part, if fracture toughness increases, strength increases as well. There are cases in some materials in which this is not the case. There can be even an inverse relationship between fracture toughness and strength. I won't talk too much about those, but just to make the point, you can rank materials, but it's not absolutely certain. You can use it to control quality. Can I tell that the material I made today is the same I made yesterday? Well, fracture toughness can be an easy way without doing a lot of strength measurements to determine whether I've made a material that's representative of the whole batch of material that I need to sell. One thing it is very useful for is predicting impact and thermal shock resistance. These are directly dependent on the fracture toughness, and so I can use the number directly in expressions to predict the resistance of my material, including the hardness and fracture toughness, to how thermal shock or impact will result in failure. It can be used to estimate what the critical flaw size I'm likely to find, because the higher the fracture toughness of the material, the larger of the flaw that I can tolerate that will cause failure. So it's a guide to the non-destructive evaluation of, if you will, what should I be looking for in terms of flaw sizes. And it can be used to understand the fundamental nature of fracture. And we talk a lot about that when we talk about slow crack growth. So again, kind of reiterating, I'll show you that in the end we won't use fracture toughness very much in terms of predicting strength, but it really helps us to understand what's going on in the material, what might be going on at the crack tip, choosing a material, looking at microstructural effects, and so forth. So there's a lot of reason to measure fracture toughness, and over the course, over the next few slides, I'm going to talk about a number of the fracture mechanics tests that have been used, that are used to measure this property of a material. And each one has its advantages, its disadvantages, to ease of use and so forth, quality of data that you get from it. And I'll try and explain that, but there's a lot more to this, and again, there's a more extensive reference. And again, I hope you'll contact me directly if you have specific questions that I can try and answer for you on any particular test. So one of the first tests that was ever used for measuring fracture toughness of ceramics is something called the notch bend test that you see here. Pretty simple. It's a bar of material that's loaded in bending. Here you see we will load it in this direction, and there's a notch here, and what we saw in a notch perhaps in a glass material, in a ceramic, and what we hope is that there's a sharp crack formed at the tip of that notch, and we assume then that the crack that we're going to use to calculate the fracture toughness is the size of the notch plus a small amount to account for the size of the flaw. But data from this test has been shown to be highly questionable. The reason being is that a sharp crack isn't always formed at the tip of that notch, or if it's formed, it's not formed throughout the entire thickness of the material. And the data from this test is variable. It typically overestimates the real resistance to fracture. It overestimates the fracture toughness of the material. And I would avoid using this if at all possible. It's a simple test, but because of these issues about the accuracy of the data, it's probably not a very good test to consider. Another test that continues to be useful is what is called a double cantilever beam test. My colleague, longtime colleague at the National Bureau of Standards at NIST, Dr. Shelley Wiederhorn, really used this test extensively to look at crack growth in glass and ceramic materials. And you can see here, the way this test works is you form a beam of material that you see here, in which there's a long axis here, and then there's a width of material here. Typically he used, advantage here, you could just use glass slides and cut them to this shape. One disadvantage of this material, I'll go and show you later, is that in order for make the crack grow slowly down the specimen or grow stably down the specimen rather than cutting off to the side and breaking off an arm, you must cut a groove. Unless you have a single crystal in which is a defined cleavage plane, you must cut a groove in the specimen in which the crack is guided down here. In the design that was originally used, one pulls on the specimen, you drill holes or in some way attach arms, attach wires and pull on this with some tensile stress, and the fracture energy of the material is then related to all the dimensions of the specimen and what is called gamma sub A, which would be the length of the crack initially. However, a number of years ago, we developed a test that would be a little more easy and more useful for use in slow crack growth, what we called an applied moment double cantilever beam, in which now we attach arms. You can see that the specimen shape is almost identical, a long axis here. Again, one requires a groove down the center of the specimen, but here the stress intensity factor is no longer dependent on the length of the crack. It's depending on the moment arm that we apply to the specimen here. So we bend these arms in some fashion, I'll show that in a moment, and the stress intensity factor at any point is related to the moment of inertia of each side of this cantilever and the thickness of the specimen T. You can see here how typically we would have loaded this little trapeze arrangement in which now you can put this in a test machine and you pull in this direction, and in this way if you rest the specimen on some arms up here, you're actually applying the moment and the crack grows down the specimen. What's the big advantage here? The big advantage is, in this case, that the stress intensity factor in this case is independent of the length of the crack, whereas in the original version it was very dependent on the length of the crack, and if you're looking at crack growth rates, you always had to be very aware and find some way to measure very accurately where your crack was in the specimen in order to get an accurate measurement of stress intensity factor. So this held some advantages, especially when we're looking at the slow crack growth behavior of materials. And I can summarize a bit of double cantilever beam testing in general. You can determine fracture toughness in this way through either one of these DCB tests. Interestingly enough, there's no standard for these tests has ever been written, but what we found over the years that fracture toughness values measured on these kinds of specimens are quite comparable to those you obtain by other methods. So you're pretty comfortable that these work well. Because of the crack length dependence of stress intensity factor, the applied moment version I recommend, because it's much easier to get the crack growth data that you need. One disadvantage of these, any of these, if you're looking at measuring crack growth as a function of time, you have to measure the crack length optically. So for translucent specimens, for transparent specimens such as glass, this works quite well. For translucent or opaque specimens, you can see the crack growing, but proper lighting is always a key to observing the crack motion. In addition, I mentioned this groove. The groove is about halfway through the specimen in thickness to guide the crack, and the groove could cause complications due to machining damage in the material, etc., etc. So This is a very useful test, for example, to look at slow crack growth behavior in materials. I would not say it's the best kind of test to get a critical fracture toughness value. In addition, introducing a crack is not easy in any of these configurations. In other words, when we go back, let's go back and look, and I'll show you a bit why that's true, how one might do it. This is the easiest one. So now I can put a little saw cut in here, but I don't necessarily guarantee myself that there's a crack at the end of that saw cut. And there are lots of little clever ways in which I can get the crack to pop out of that saw cut. None of them are easy. One loses specimens in putting the crack in, etc. So it's possible. It's been done lots of times, but it's not the most easy procedure in the world. So let's move on then to other kinds of tests that maybe are a little easier, particularly if really what we want is other kinds of data. Now here's an interesting test that we used for a number of years because again, like the applied moment test, the crack will grow slowly down the center of the specimen. As it turns out, in the double torsion specimen, I don't need a groove. The geometry is such that I apply a torsion, or there's a twisting motion to each side of this beam that you see here, and the configuration is such that the crack naturally wants to grow down the center of the beam. Here's the expression that you use to calculate the stress intensity at each point, and the stress intensity factor is independent of crack length. And there's a very nice review of the double torsion specimen that I give the reference here, and I would encourage you, if you want to use it, to go look at that. So, but there's advantages and disadvantages. Again, crack stress intensity is crack length independent in this test, very useful in many applications. All loading is in compression. Makes it very easy to load up and do tests in an environment, do tests at somewhat elevated temperature because you don't have to attach anything to your specimen to get your data. A very nice feature of that particular specimen configuration. So again, there are ways to do this test. I'm not going to show you the details. I would encourage you to again look at that reference, but the crack growth data can be obtained without actually seeing the crack grow. One actually measures the change in compliance of the specimen with the loading on the plate itself. And so again, it's useful for testing at elevated temperatures or harsh environments. You can put it in an enclosed container and get data on crack growth. But it's useful for materials such as concrete, where the large size specimen can be prepared, but for many advanced ceramic materials, or where I make bars or other strange shapes or spheres or whatever, it requires a lot of material. And because it requires a lot of material, it can be an expensive test to run. So if I'm making plates of material of any kind, I can cut double torsion specimens and be very comfortable that I'm going to be very efficient in getting the kind of data I need. But if I'm making other kinds of shapes, it is sometimes quite difficult to get a large enough shape to conduct this kind of test effectively. So like anything else, it has its advantages and disadvantages. There are several, though, ASTM standard test procedures, and I'll just briefly go through those. For instance, this is what is called a surface crack and flexure. At the end of this series of lecture, and this lecture in particular, I will give reference to all of these ASTM standards, and I strongly encourage that if you're going to conduct this test to go to that and follow that procedure, and it gives you quite good data. This is a very nice test for getting fracture toughness. What one does is put a NUP indentation, for example, in the surface, a polished surface of the material, and this then produces this crack, a small crack on the surface. The next step is to polish off the damage that you produced during the NUP indentation and break the material in 4-point flexure. And based on the strength of the material, and I don't give you the equation here, but one can calculate directly then the fracture toughness for this kind of specimen. And that kind of data is very accurate. It has become the basis for actually a standard reference material issued by NIST, and a very reproducible kind of data on ceramic materials. This was on silicon carbide. So a very good test, and I encourage you to go look at the literature and use that if necessary. Another test which is used extensively for various reasons. One, because it's very easy to conduct, and it's become very popular, but there are several limitations to this test. Let's talk a bit about this technique called indentation crack length. It's a very popular technique, and probably with good reason. It's very useful, for example, if you have very small amounts of material, very small specimens, etc. It's, in principle, quite easy to use, and it consists of putting a Vickers hardness indentation into the specimen, similar to what I showed in the earlier test, but in this case, instead of polishing off the damage caused by the Vickers indentation, I make use of the stress field introduced by that damage in the expression that you see here and the original reference to, I think the best one to the expression for calculating fracture toughness from it is the one that you see here. One then measures the length of the cracks emanating from that indentation in this way, and one can calculate the stress intensity, the critical stress intensity, if you will, from an expression like this, where C is now the length of those cracks. But there are several important considerations you have to think about here. It's not really consistent. The number I get for stress intensity or fracture toughness can't be really consistent with that definition I gave earlier, where the crack grows rapidly at the point of criticality, because in this case the cracks grow quickly at the beginning, slow down, and then stop. So sort of by definition the two numbers are not going to be quite the same. Will that make a difference? Maybe, maybe not, but one should recognize that I may not be getting the same kind of number. In addition, the crack system can be very complex. Any of you who have put hardness indentations into ceramics know that it produces damage at the site. There are what are called lateral cracks, which are parallel to the surface in which I'm putting the indentation rather than perpendicular, which I use to calculate the fracture toughness. They can interfere with my calculation of the fracture toughness from this particular technique. There are many expressions to calculate K1C from this kind of procedure. The one I showed on the slide a few minutes ago is probably the most accurate, but it turns out that they're not consistent with one another. Every one of these expressions will give you a different value for fracture toughness. So let me talk about a few considerations when you're using this test. Maybe it's the only test available to you because you have very small pieces of material and you need a number. And this test will give you a number. But the inaccuracy can come from a number of reasons. One, the so-called lateral cracks, which are parallel to the indentation surface instead of being perpendicular to it, can change the damage zone and therefore change the driving force on the crack. As I mentioned at the beginning, none of the expressions used to calculate fracture toughness are fundamental in nature. They're derived in various ways, and they differ from one another. And so you think, well, can I use a test to rank materials? And there's an interesting article by Ponton and Rawlings, and I show their reference at the end, that this is also questionable, that depending on the expression you use to calculate fracture toughness from this test, you can get different rankings from one material to another. So these are just notes of caution. I don't want to stop people from using the test. I've used it myself to great effect because I had no other way of actually getting any number to measure fracture toughness of a small amount of material. There's another material I want to talk about briefly, which is called indentation strength rather than indentation crack length. And in this case, I put that same indentation into a bar of material and I measure the strength as a function of the indentation load in which I put the indentation, and I get a series of curves that look like this. If I have a a large crack out in this regime, this expression would say that the relationship between the strength and the indentation load should be to the negative 1/3, and if material is behaving correctly, that's what I see. And as I get smaller and smaller with indentation loads, what we call natural flaws in the material cause failure rather than the indentation itself, and the curves flatten out and you see behavior such as this. And these shaded areas represent entire failures from what we call the natural flaws, the flaws caused by machining and so forth. It's not used very often, but it can give some useful information. It's again empirically defined. The constant in front that you saw earlier, there's considerable variation around the number. It was obtained using empirical data. The slope of the curve must equal a minus a third because that's represented from the equation that I derive it. And if you get deviations from that slope of a negative 1/3, it's an indication that other effects are taking over. And so it can be used a little bit, but not too often. Let me just summarize then what I think we've talked about a lot during this particular chapter in the series of lectures. One, I think most important, just get this idea across that the development of fracture mechanics was the key to our ability to both understand the fracture behavior, to understand the physics of fracture, and to quantify the fracture process. I showed a number of procedures for determining the important fracture mechanics parameters, particularly critical fracture toughness. I did not show all of them. There are others out there in the literature, maybe less used because of their difficulty, the complexity, and so forth. But I showed more of the common ones. I wanted to make the point that fracture toughness is not a fundamental parameter of the material. It is dependent on the particular test I use to determine it. And so one has to be careful from that point. There's uncertainty of it. And something I'm not going to talk about, I show here a number of pertinent references. I would encourage you to take a look at those, and if you have any questions or want to know other data about them, to contact me and I'll try and help you out. So this kind of concludes the first part, the first lecture in this series on the development of fracture mechanics and fracture mechanics tests. In the next part, what I call part 2, I want to talk about environmentally enhanced slow crack growth, and particularly go into a great deal of detail on what goes on during this process.